So welcome back, and in these notes we're going to be looking at the aromatic group. That's benzene and phenol. Now you've come across benzene many times before in organic chemistry, but you haven't studied it in any detail. And in this first video we're going to be looking at the structure of the benzene ring and why and how we know it has the structure that it does. So for a long time we knew that the molecular formula of benzene was C6H6, but people struggled to come up with a structure for this molecule. Then in 1865 Kekule proposed this structure, a hexagonal ring of carbons with alternating single and double bonds. And in many textbooks you will still see the ring structure drawn out like that, and it's perfectly acceptable in your exam to draw it out like that. But we do need to understand that that is not actually a good representation of the benzene ring. And there are several pieces of evidence that show us that this is not the actual structure. So our first piece of evidence comes from X-ray diffraction studies. Now, our proposed benzene ring, our Kekule structure, had alternating single and double bonds. So an isolated carbon single bond would be 0.154 nanometers. An isolated carbon-carbon double bond would be smaller because it's a shorter bond, 0.134 nanometers. But actually, when we measured the carbon bond lengths in benzene, they all had the same length. They were all 0.139 nanometers. In other words, they were all shorter than a single bond but longer than a double bond. And in fact, if you looked at the electron density map of benzene and you draw in the hexagon, you should be able to see that these bonds are all the same length. So a more modern image is here below, and you can see again that all the bond lengths are equal, and they're sort of in between a single bond and a double bond in length. And that was one of the first pieces of evidence that tells us that benzene does not have alternating single and double bonds. So just to remind ourselves, the definition of the enthalpy of formation is the enthalpy change when 1 mole, in this case of a liquid, because the standard state of benzene is a liquid, formed from its elements in their standard states under standard conditions. So here is our equation. We have 6 moles of carbon in its graphite solid state, reacting with 3 moles of hydrogen gas to form 1 mole of benzene liquid. And we're going to use this data to work out the theoretical enthalpy of formation of benzene if benzene is something with alternating single and double bonds. So I'm going to draw out the Hess cycle for the enthalpy of formation of benzene. So I'm just going to rewrite that equation. So I've got 6 carbon solid atoms and 3 hydrogen gaseous molecules, and that's going to make C6H6 liquids. And I've been given atomization values and bond energy values, and in all of these cases I'm going to end up with the gaseous atoms. So I'm going to have 6 carbon gaseous atoms and 6 hydrogen gaseous atoms. And I can turn those into that by doing bond energy calculations, and I can use those into that using atomization. So I've got my enthalpy of formation. I'm going to call that delta HF, and I'm going to label this one delta H1 and delta H2. So using my knowledge of Hess cycles, I can say that delta H of formation is equal to delta H1 minus delta H2. And as I said, in this example, I'm going to assume that this is this Kekule structure of alternating single and double bonds. So I'm now going to calculate the theoretical energy change. So I'm going to calculate first of all delta H1. So I've got to atomize 6 moles of carbon. Well, to atomize 1 mole of carbon is 715, so that's 6 lots of 715 kilojoules of energy. And then the next one we've just got to be a little bit careful with. We're given the enthalpy change of atomization of hydrogen. Now this is the one where students get it wrong because they times the number by 3, but it's not, because it's per atom. So it's 6 lots of my atomization of hydrogen, which is 218. So that added together equals, and I get plus 5598 kilojoules per mole. If I work out now delta H2, that's this Kekule structure. Well, I've got 6 carbon hydrogen bonds, so I've got 6 lots of 413, and then I've got 3 carbon single bonds, which is 3, 4, 6, and 3 carbon-carbon double bonds, 6, 1, 0. And again, I'm going to add all of those together, and I get 5, 3, 4, 6 kilojoules per mole. Now my delta H of formation is delta H1 take away delta H2. So I get 5598 take away 5346, and if I put all that into my calculator I get plus 252 kilojoules per mole. In other words, if this was the correct structure, making 1 mole of benzene from its element under standard conditions would require 252 kilojoules of energy. When we actually do this in reality, and we do the experimental value, so the experimental value is plus 82 kilojoules per mole. In other words, I'm missing 170 kilojoules of energy from somewhere. Obviously, we know it can't be missing because we can't create or destroy energy, but we need to understand why our experimental value is so much more exothermic, so much closer to being an exothermic value than the delta H formation calculated using this structure. So our theoretical value equals plus 252 kilojoules per mole. The real value is 82, so there's 170 kilojoules per mole of energy which appears to have gone missing. It's not really gone missing, it's just that the real benzene structure is much more stable than expected, because the enthalpy of formation is closer to being an exothermic reaction. It's still endothermic, but it's much closer to being exothermic. So therefore the actual structure of benzene is much more stable. And it's easy to see that on an enthalpy level diagram. So if I draw out the enthalpy level diagram, we have 0, that's the enthalpy of my elements, my 6 carbons and my 3 hydrogens. The Kekule structure here, well, to get to that structure, that is a change of plus 252 kilojoules, but if I go to what we now consider the real structure, this structure, it only takes 82 kilojoules per mole. Remember, the further you come down, the more stable you are. So this is more stable than this because it's further down. Obviously, exothermic reactions are even further down, so they'll be even more stable. So the third piece of evidence comes from IR data. So here we have the IR spectrum of benzene. We have a CH stretching here, so that's my CH, and that's at 3030. Then we have an aromatic stretch at 1 500, so that's my C double bond C. We can compare that with oct-1-ene, so an alkene, and it has a CH stretch here, and that's in the range 3095 to 3010, and it has a C double bond C stretch. Here's my C double bond C, and that's at 1669 to 1645. So it's slightly higher than the C double bond C stretch in the benzene ring. So the next piece of evidence comes from the addition reactions. So when we add hydrogen to an isolated zinc double bond, so for example when we add hydrogen to cyclohexene to make cyclohexane, it releases 120 kilojoules per mole of energy. Now if benzene was this K-cure structure, these alternating single and double bonds, we would expect the value to be 3 times this value because we would have 3 double bonds to add hydrogen across. So we would expect to release 360 kilojoules of energy. So this reaction should be exothermic, and it should be exothermic to the value 360. Actually, when we add hydrogen to a benzene ring, it's not easy to do it, but we can. We only get minus 206. So we seem to be missing again some extra energy. We're missing this time 154 kilojoules of energy. What's actually happened is that energy can't disappear, but it is needed to overcome the delocalization of the benzene ring. And our last piece of evidence comes from isomers. If benzene had this alternating single and double bond structure, we would be able to get 2 isomers. One here where the CH3 groups are across a single bond, and here where the 2 CH3 groups are across a double bond. And those 2 isomers would be different from each other. Actually, only one form of this molecule exists, 1,2-dimethylbenzene. So what's actually happened is the p electrons in the carbon's outer shell has actually become delocalized over the whole ring structure. So those pi electrons are all delocalized. And that's why we quite often draw the benzene ring like this, showing a ring of delocalized electrons. And that's going to make the benzene ring much less reactive than you would expect, because those electrons are delocalized. They're not localized to a double bond, they're delocalized over the ring structure. So benzene is much more stable than you would expect it to be. So it's always good to have this little phrase whenever you're talking about why benzene is more stable than expected. So this is a nice little sentence, and always you start with, no matter what evidence you're using, to explain why benzene is more stable. Because the 6 p electrons are delocalized over the ring. So they're kind of smushed out so that they're not concentrated, and therefore it's much more stable than you would expect. So here are my 5 pieces of evidence. X-ray diffraction, all the bond lengths are the same, and they're intermediate between the single and the double bond. In terms of thermochemistry, in terms of the energetics calculation we found that the benzene structure was much more stable than you would expect when it's reacted from the elements. The infrared data, we saw that the vibrations were in different places in the alkenes compared to benzene. When we added hydrogen to a benzene ring to make cyclohexane, we saw that we released a lot less energy than we would expect. And we didn't get these isomers, so these 2 isomers are identical. So we're putting all those pieces of evidence together to show that benzene, although we can often draw it with those single and double bonds, is actually contains a ring of delocalized electrons. And that makes it much more stable and much less reactive than you would expect.